as a way to wrap up this course, thanks for sticking with us this whole time. We thought it would be nice to take a step back and sort of put things in context a bit. So we've talked a lot about the oceans and climate change and how those two things are sort of interconnected, and how the oceans impact the climate and how the climate change will impact the ocean. But we've just scratched the surface there. So there's a lot of different things that are happening that we haven't even touched on. So for example, there's projected sea level rise. Sea level rise is a result of the ocean's warming, and so thermal expansion occurs. As water warms, it expands and fills a larger volume. And there's also land ice that's melting, so the ice is melting and running off into the ocean. Another big impact is ocean acidification. So CO2 dissolves in water and creates carbonic acids. And this acid can dissolve the shells of marine creatures. And this has a really big impact on how much CO2 the ocean can continue to take up, as well as the biological productivity of the ocean. There's also past large extinction events due to warming and oxygen loss. And so a lot of species went extinct during those high CO2, high temperature, low oxygen events. And a lot of species were displaced from their habitats, having to move to more friendly conditions. And then sea ice extent. So that's due to warming oceans and currents bringing warmer water to where the Arctic sea ice is and melting the ice. So we can see here there's a trend in decreasing September, which is usually the maximum in Arctic sea ice. I also really wanted to talk a bit more about how much CO2 concentration in the atmosphere matters. So I mentioned that currently we're at about 415 parts per million of CO2 in the atmosphere. In order to stabilize our CO2 concentrations, say at 450 parts per million, we need to actually immediately cut emissions, because stabilizing emissions increases concentrations. Actually getting CO2 concentrations in the atmosphere to stabilize requires decreasing and halting emissions. And then there's a lot of different time frames when it comes to CO2 and temperature and impacts. So like I was just talking about, if you want to stabilize CO2 concentrations, you need to stop emitting CO2. So this brown line here is an idealized curve showing CO2 emissions. So say we have some sort of peak and then we decrease emissions and stop emitting altogether. This purple line shows the CO2 concentration. So concentrations continue to rise even after CO2 emissions fall. And then finally, concentrations stabilize as CO2 emissions go to zero. This red line here shows the temperature response. So the temperature continues to rise fast at first and then slowly, and it takes a few centuries really for the temperature to stabilize. And then this blue line here, this solid blue line, shows sea level rise due to thermal expansion, and that lags temperature. The ocean is sort of sluggish to warm in comparison to the atmosphere, so it takes a longer time to stabilize. It takes 1,000 or more years. And then take a look at this dotted blue line. This is showing sea level rise due to land ice, like Greenland and Antarctica melting. And glaciers are even slower to warm and melt than the ocean is to warm. So glacier stabilization and ice melting takes thousands and thousands of years to finally come into equilibrium. So this, I think, is a good argument for why CO2 emissions must be cut and we must try to go to zero as fast as possible. This is a comic that I like by XKCD. And so we've talked about how the global mean surface temperature has increased by about 1 degree Celsius since 1850. And we all have also seen that under some of the representative concentration pathways, particularly the higher emission scenarios, the projected warming is about 4 or 5 degrees Celsius by the end of the century. So what does that even mean? The Earth was about 4.5 degrees Celsius colder during the last ice age. And during the last ice age, Seattle was under about a kilometer of ice. So that's a pretty drastic difference from how the climate is today. Another example is when the Earth was about 9 or 10 degrees Celsius hotter than it is today. And that was like a hothouse climate. And the sea level was about 200 meters higher than it is today, which is a big difference. And there were palm trees and crocodiles living at the poles. So 4.5, 5 degrees Celsius is really a big difference in the Earth's climate.